Okay. Yeah, so let's start with the recur what we have covered last week, if that's okay.
Yeah.
Good stuff. Yeah, so we touched the fully connected feed-forward neural net last week, and that was just this picture. So we give inputs, then the input goes to each neuron, and then each neuron is actually the logistic regression, as we touched last time. So I think I just simply saying this is linear algebra. So each neuron has linear algebra, and we have an estimated output at the end. So it's going to be 0 or 1. And yeah, so we train the neural net to find the best W weight and the bias, the constants. And that was last week. And so we understand what is the concept of neural net now, but how can we train that? That's kind of a big question there. So neural net is not exactly a convex optimization problem, which means we can train and we got the kind of pretty good performance, but then it turned out it wasn't a global minima. And so it was local minima. It means we only had the local optimization, not the global optimization, which doesn't necessarily be too bad. But yeah, just to keep in mind that the neural net, might need more experiments. That's it. And we mentioned about overfitting last time. So the approach here, I'll just simplify the definition. So approach, we can just think like the number of training we gone through for each data set, just simply say. And so yeah, number of training we've gone through for the model. So what we will do is we don't want to overfitting. So I will compare the performance each time I train the model. So as we mentioned, we will build a model with the training data set. And we'll go through the training again and again and again. And we will calculate the performance or the error rate. And also we will compare the error rates based on the validation data set. So we'll see what's the performance like. So once we know the validation data sets doesn't perform as great as before, then we know it's the time we stop the training. So around here. That was what we mentioned last time. And so is a neural net so great? Yes, it is really good. It can give you really good prediction. But then the problem is neural net typically requires a lot of training. So it takes a long time and it consumes your resources as well. And the more importantly, yeah, it's data hungry. So you really need a lot of data if you want a good performance over the model. So there's a research, I think you know that as well. So the published research, published paper, and what they experiment was, so they had they just compared the performance of each models. They had several different models. And then they compared the data size. So the amount of data they feed for the model. And the research was pretty interesting for me. So they're really fancy models, maybe perform like really great. It's much better than kind of simple models and so on. But then the performance wasn't really significant, considering the type of models, but it was actually more important that the amount of data they feed for the training, that was actually more important. So because it kind of gives you a curve. So let's say you have a simple model, but you have good enough data, then you can kind of expect a good performance. But then you have really fancy algorithm, but you don't have enough data, well, your performance could be pretty bad. So I say, yeah, data and a lot of data. If you can get, you can pick fancy training model.
Yeah, just to add a quick point, like sometimes you want to build up on a specific algorithm, you might not need to have like your own customized data. There's a thing called knowledge transfer in neural networks where you can use the weights trained by the people already, and then you can just change the few of the layers, like the end layers that basically categorizes. So in that case, you don't have to train like billions of parameters. You can rather can use like the trained models that people have already trained with like terabytes of data.
Yeah, actually, that's really good point, Yash. I really like that you mentioned. So this was a big challenge over the machine learning. So I think the big question was, how can we reuse the model? And so as Yash you mentioned, there's a good libraries that they share the trains, the parameters, and they actually perform really great, and we can reuse our ways all the time if you like. Yeah, that's really good point, Yash. Thanks.
You're very welcome, Nare. I think in the previous slide, didn't want to interrupt in the previous slide. Previous slide, you mentioned a couple of things like, so you mentioned convex optimization problem, you mentioned about overfitting. However, there was much information in the slide. So it'd be great, like, when like you can just give a like slide overview about like these points so that like even someone gonna watch these videos would better understand because you might know like more about convex optimization problem, someone might not know what you meant there by overfitting, and then like and what impact it has on validation and training data, and then why you have to stop that, and epochs and stuff. So like quick overview would be like convex optimization problem, like any mathematical function whose second derivative is like is zero, like so check the second derivative less than zero, then you got to know like it's a global minima. And in neural nets, like the function that we come up with, like its second derivative doesn't fit the criteria of being in a convex optimization problem, and that's why we don't know whether it be a local minima or global minima. And the problem with that is like if you've got local minima, then basically you are just trying to update weights for you would reach to a point when you're optimizing your function, which is a local minima, so which might not reduce your error to the absolute minimum of that function. Rather, you'd be happy to have an error which could just be local minimum. So you could like keep going ahead with like training, and you can get like a better performance if you reach the global minimum. Yeah, that's it.
Super. Thanks, Yash. Really, that's really good. Yeah. Thanks.
Yeah, now you can go ahead.
Cheers. So this is very exciting part from now on. So let's touch the deep learning part from here. So the deep neural net. I was so excited to learn about deep learning because it's like a big buzzword, and I was like, oh, Jesus, I have to learn deep learning. Then what I learned was actually kind of funny, because they said, okay, the deep neural net is actually neural net. We just covered the feed for the neural net with more than a small number of hidden layers. So if you have like a really many numbers of layers, we just say deep neural net. I was like, okay, good stuff. But why do you even bother to name it? But then they actually said number of layers are very, very important. So say, if you have more layers, then the overall size of the network, the overall size of the network, the number of neurons and stuff can be reduced for a given overall complexity. So for the same issues, same problem, you can reduce the complexity and reduce the number of neurons if you have more layers. And if you think about it, it kind of makes sense because, okay, we said each neuron is a linear algebra. I just simplified that. And then if you combine two linear algebra, let's say, then you can express maybe like second order equation, right? Sorry, second order equation. I don't know, like if it's right term to explain what I'm trying to say, but you know, like simple equations combined, and then we can expect better or more complicated equations. So that's kind of the concept. And actually, what they are saying is even better. So there's a universal approximation theorem, and it says with 2 layers and the unlimited number of nodes per layers, then you can approximate any kind of function, which sounds very, very exciting. So the key point here is more neuron, more nodes, or the more layers, you can express like a much rich kind of function. Yeah, that's the kind of keyword here. And this deep neural net or deep learning is very efficient for perception tasks. So like image or audio, that kind of complicated tasks. It's very good. And another kind of variant of deep learning is convolutional neural net. It's called CNN in many cases. So someone just say, okay, I have image data, and like it's some kind of metrics, like a 3 by what's it called? Yeah, it's 3-dimension metrics. And some smart people just thought, well, isn't it fair if we considering the pixels where sit beside each other rather than just random location from here to there? Isn't it better just considering all together here? So that's the idea behind of CNN. So we have a small filter, or just say filter here. I don't know, like we can probably call the convolutional layer. Then they just calculate its local data and calculate the output. And it's the same as the neural net we just touched. So you just like calculate just like a dot product and then just, get the output. So it's another linear algebra. So yeah, you're right. It's locally connected neural net, and the filter, this guy can be called a feature detector because it can feature detect. I'll just explain here now. So I like this example. Let's say we have an image of a car, and with the convolutional neural net, we can detect a low-level feature with the filter we just seen. So what it means is, okay, this is low-level feature. So this neuron probably has ability to detect a sharp edge, and maybe this neuron can maybe detect a like round or like circle, not like a pointing edge. So then at the end, after some layers, we can get the higher level feature, which is like, okay, this neuron can detect, oh, this is wheel. And this neuron probably can detect, oh, this is a red number, or this is a mer. And at the end, what we can get is, oh, I see. So this picture is actually a car. Or it can just say, oh, it's actually a house. You know, that's kind of CNN. Yeah, is that okay? Or any questions here?
No, I like it. I like the slides and the way you're explaining it.
Thank you.
I think, okay, so like, if you don't mind, I'll just add like quick explanation there, like on
Yeah.
the CNN part. So apart from CNN, like if you think of any of the neural network problem, what will we do? Like we take the input, it could be an image, it could be a voice recording, whatever it is. And we have to, like format it into a specific, specific dimensions. If you've got, let's say, vector of 1 is to like 100, and then we feed that into our neural networks, and then basically the whole data get propagated and we got the outcome. And now if you look at the images like just 2D data, and let's say we've got like 100 by 100, so we've got like what, 10,000, like vector 1 is to 10,000, we got to feed the whole thing into neural networks. And images are full of like, noisy data, extra data, unnecessary data, like put a background in, like if you took a selfie, there's a person in the picture, but probably like 50% of the picture is just by the background, like blue sky. So that information is like useless. So it doesn't make sense that we just like transform the each image and then fed into a neural network and then expect that our algorithm going to perform well. So what do we expect is like, we try to find the features in the image. The features are like what, if you are hovering over an image with a sliding window and you see that there is an edge where like, half the section is covered by the black, half the section is covered by white, so it could be an eye. So basically these are the mid-level, high-level feature that we are talking about here. Features are an image, could be edges, could be boundaries, it could be, anything where there's a spatial change in the color. So all are these features that we are more interested in when we are trying to identify someone in the image. And that's where we use neural networks. So what do we do is like, if you go back to previous slide, these filters that you have used there.
Oh, sorry, you're talking about this guy, is it?
Yeah, so the orange small filters that you're talking about, like I think in computer vision language, they're called kernels, and then they're filled with like random integers. And what their job is that, let's say if my image is based on like it's RGB image, the values go from 0 to 255 for each pixel. And if you got these 9 pixels and this sliding window, hover over to them. And when you hover over, basically you do convolution between this kernel and that segment of the image. It's just a mathematical operation, gives you one integer value. And now you realize that everywhere you have, let's say, an eye, or you have an edge, really sharp edge in the image, and you hover over this kernel, it gives you a very specific integer values, which could only be possible with the edges. And that's how we got to know that, okay, this value could have been an edge. So the pink part we've got here is the feature map. When we hover over, we've got the feature map. Now, the best part of that is that we were talking about, we have reduced the dimension of the actual image. So we don't have to fed into the entire image now. All we've got is the feature map that basically has a map of that specific feature we are trying to detect. Would it be an edge, or would it be a line, or would it be a circle? So this kernel, you see there's 3 kernels there. So one for each RGB. In convolution neural network, if you're working on a customization problem, let's say I'm working on something whose job is to detect guitars. Now I know in guitar there's a very specific feature that there would be a like how would I say, there would be a fretboard. So fretboard size of the fretboard would be smaller than the entire hull of the guitar. So I can develop my own feature, like took an image of like the guitar, and then like I say, what are the values of these filters, kernel values that we are talking about? What are we trying to detect that would make our life easier and like make our algorithm works better for guitars? We don't want to like run it on people or like phones. We just want to run it for guitar. Like, so if there's a specific problems, we can create our own kernels, filters, and you can use as many filters as you want. The benefit of those would be you would have like as many feature maps that you want, and then you use these feature maps to fed into your deep neural networks that we have previously seen. And I think that's how it's able to like detect that could it be a person, or would it be a guitar, based on these feature maps. And also like we can cut this from any part, like if you like very really long, really deep neural network, we can cut this from a specific layer by saying that, okay, the output of layers up until this point is the feature maps that detects edges. Now you can use this information in any context after that, that what do you want to detect? Do you want to detect cars, or do you want to detect persons in this? It's up to us. So you can also add additional layers based on the problem you're trying to solve. But yeah, that's it. I can go ahead from here now.
Very good, Yash. Really, really good insight. I really like that. Thanks. Big
You're
thanks.
very welcome.
Super. Yeah, that was very good. I know, Yash, you're gonna touch the recurrent neural net maybe in 2 weeks' time. But I'm just gonna give real quick overview because I wanna explain about the long short-term memory, because I implemented this model to the stock prediction project. So just a quick one. So there's so-called recurrent neural net, as this name implies. It's kind of recurrent. Okay, so this is actually the same as the feed-forward neural net, except this cell can go backward, not just the forward, but it can go backward, which means we can memorize some sequence there. This is really brilliant idea. So let's say, all right, looks interesting, but let's see better view. So we unfold this one, and we got the kind of sequential structure here. So what we give them is the inputs of the sequence. So this, maybe you have an idea, like maybe previous data and the next data and next data and so on. And it goes to a cell. Yeah, you can think as a kind of neuron here. So it's a cell, memory cell, and it gives you the output. Probably some people might think, okay, I think you better use Y here instead of H, and H goes here because H is for hidden layer. It's up to people, but so it gives you the output. As you see, the output, well, the calculated output based on the previous data is actually going to the next calculation as well. So as you see, like some time step or some sequential point here, they would have a kind of previous data from the previous calculation. So we are saying it has a kind of memory. That's the recurrent neural net. And
1 second, before like go to the next slide, because LST I'm gonna be like super heavy on people when they hear about it, all the gates and stuff they're gonna hear. So it's like you explain like how it's being structured. I'll just add on to this, that what the use case of it. So let's say you are solving a problem about, you mentioned about the stock market. Now, in order to decide like stock price, you got to know the historical values of the stock prices as well. So if you ask your like your neural net to predict that what will be the price of the stock, like in future, like probably tomorrow in 5 minutes down the line, got to know the information from these previous values, and whatever being predicted at this timestamp t might be useful in the future timestamps. Same thing with the with your natural language processing, where we use RNNs. Is if I'm saying machine, like I'm saying the whole thing that machine learning is a really cool subject, and if you're using this to predict that what topic are we talking about, and let's say this is the algorithm that basically picks out the topics, or it could be about machine learning, how are it going to know that it's about that? When you're going to feed like one word at a specific timestamp t, so you got like t0 machine, t1 learning, your algorithm might predict the machine is like a device, and learning is like something educational. What machine learning altogether makes like completely different sense. It's itself is a word, and it's a subject in the computer science. So how does it know that? So when it's processing learning, it's vital that it should know the information from the past that it had seen before, and then it trying to trying to make more sense that what could be the collective meaning of that word. And that's where we kind of need the recurrent neural networks, that wherever our algorithms might need historical data to predict at timestamp t, we use recurrent neural networks. And NLP and video processing and audio processing are one of the big examples of RNNs.
Yeah,
No,
brilliant. No, it's perfect, brilliant. Yeah, you're right. So it's really for kind of sequence data. And actually, I'm gonna trigger sorry. Yeah, there was a kind of issue with this recurrent network when there was a lady, I think, and she tried to predict the next word of a kind of long paragraph. She didn't find it really good performance over the RNN. And then she realized this RNN and only has the capacity of a kind of short-term memory. So then people tackle the issues.
Yeah.
Yeah, Thursday morning heart. Yeah, sorry. So they tackle the issues with this long short-term memory cell. So as it's the same as cell here, the memory cell, but the beauty of this or LSTM is that they can hold a long-term memory. I know, yes, you kind of learned that probably I have to talk about like forget gate, input gate, output gate. I'm not gonna do it here. I'm not gonna do this, but just a really high level overview. So this cell, memory cell, is for the recurrent neural net, but then this C is actually a long-term the states. It can hold long-term states, and this H, the hidden one, that is they can hold the short-term state. So in sequence, you can see the input is coming, the sequential data is coming to the cell, and yeah, they can give the outputs here, but the output actually goes to the next cell, and also they didn't forget the long-term memory. So long-term memory goes in, short-term memory goes in, and they calculate like heavy stop in the cell, and then they predict the next one. So that is LSTM.
Yeah, interesting. Yeah, you covered like a very important point there. Like, so it's like it covers like long term and short term memory. So you said like there's a problem with like short term memory, and it makes sense because every time you feed something, like, you know, if I ask you, Nare, okay, Nare, from now on, Tesla price gonna go up tomorrow, okay? But you need to know at least like 2 years historical data about Tesla. Now it's impossible that you're gonna remember, say, like, you know, 700 days of data about Tesla. You might remember like last 5 days over the stock price for Tesla. So what's the problem here? Because it's not feasible. The same thing when we're trying to solve a problem with recurrent neural network, and let's say we ask a neuron to remember all the historical data, it's impossible. Basically, it's like more and more variables. We can't remember like, you know, infinite number of all data that we've already seen. And as we've seen, like, it's a sequential, it takes a sequential data as an input. So there's no end to the historical data that we have seen. Could be like 500 characters to like thousands of characters. So of course your neural network is going to only remember to like a certain extent in the past. And there was a problem of the short-term memory that you mentioned, you know, like that, you know, they can't remember, like if I'm talking about Nare, and then I mentioned very beginning that she is a female, but after that I wrote a massive book about Nare where I didn't mention anything about that she's a girl, and my neural network is supposed to predict that what like whether she's a girl or not, like, you know, and it's seen like what 50 remember like 50 or 100 characters in the past, then it's impossible because it forget what it had seen in the very first thing, which was the most critical part. So I think in long short-term memory, what we're trying to do is we're trying to remember stuff, but we can't keep them all like, you know, 100,000 words that we have seen before. What we can keep is like we keep updating what we remember, what we remember. Like, so if we like save Nara is a girl, which is an important thing. We shouldn't forget. For next like important thing that's gonna come, we keep adding it. Or
Yeah.
we don't add like random stuff that's coming in, like almost every single word. So in that way, like there's multiple gates that you were talking about, like update gate and forget gate and stuff. Basically, they wrote like a lot of mathematical functions.
Yeah.
Each time it predicts something. It basically decides that, oh, should I add this into the state C? So you can see like C T minus one. So basically, C is like your state, like what, like it's a bank of memory that
Yeah.
like you have capped like that. Okay, that's what we know. So you decide like at each time that, oh, we predicted H, some
Mm.
HT, and should we keep it into this in like in our what's called state, I think it's
Yeah.
called.
Yeah.
Should we store it, should we update it, or should we forget something
Mm.
from the state, or something might not be useful. So all these happen due through these gates, which are just like mathematical expressions.
Yeah.
Very well presentation. Now you can take from here.
Thank you. Appreciate it. Okay, so just a quick one here. So we mentioned about overfitting, and we understand this is a big issue. Okay, then how can we fix this? So one of the techniques to tackle this issue is early stopping. So yeah, kind of makes sense. The name kind of explain everything. So we test the current network on the validation set. We know this part. So we train the model with the training data set, but also we calculate the performance after the training with the validation data set. So we know what's the error rate or the performance like. So that's the meaning. Then we compare the validation set performance, this curve, red curve. And at the current time with the performance from the last time. Okay, what it says is, Gustav, like we are training and we get the error rate each time, but then don't just override your the weights or the parameter setting. Don't just override, but just always compare if the performance of the validation data set goes any better. If the performance improves, then override your variables, other parameter setting. And that's kind of the thing. And so we might decide to finish training around here because we've kind of found the performance going really bad. Like we kind of found the signal of overfitting. So we stopped around here. And then we don't just get the parameter we just found is from here. Actually, what we get is the best one we found here because we only save the model parameters at that stage when performance gets better. That's early stopping. I just mentioned this one specifically because that's what I'm going to use for this talk prediction, if that's okay.
Again, overfitting word, like can you explain a bit more about like what's
Yeah,
overfitting?
sorry, I thought we captured last week. That's why I kind of didn't mention it.
No, in just today's session, like just don't like go in detail with overfitting. Just like quickly say that overfitting is like does it runs well on training data but doesn't do well on the test data. And then we don't want our algorithm to basically overfit that it just works well with the training data set. And that's where like you want to stop early. And what parameters you use to stop early, you just see that okay, it's working fine with training data, so my error is reducing with training data on each epoch, but my validation started increasing, like the validation error started increasing. It means that it's working pretty well on training data, but it's not working on unseen data. That's what we use validation data for. Like, okay, we've got like a set of data that we're going to train you for, and then at the same time we've got this unseen data that we're going to test you while we are training, and then we'll have a test data separately, which would, once we are happy with our model, then we test it. So that's where you are using those curves that like as soon as like the validation curves start going up, you realize that okay, it's working really well with the training because error is still reducing, but when the validation error is increasing, it means okay, it's not working well on the unseen data, and that's where could be a problem of overfitting, and you stop early.
Yeah, good stuff. Yeah, just quick recap here. So the overfitting. So let's say we have a true function here, the green one, and we train the model, which is red one, and we train over and over and over again. So now my model can predict very well, like 100% accuracy here, because I trained a lot and I got this lovely curve in red. But then the problem was that was trained for a noise, which shouldn't have. So at the end, what this model, my red model predicts is like completely out of the kind of expectation. So then what did it happen? Because we trained too much and my model trained for noise. So that was the issue. And as the kind of this situation implies, the performance can go really good if we train over and over again, or if we use the complete complex algorithms. It like a high chance they will give a really good performance. But then the problem is, as Yash said, if there's a kind of unseen data, then it gives you really wrong. It can give you really wrong outputs. So we don't want that. Like we put so much effort to train model, but then what it gives you is like completely,
Yeah, we don't want a kid that memorize everything, but don't have its own. Like it can only tell you what it memorized.
Yeah.
Not anything else. Like these kind of students always fail in the exams because if something comes up from out of the syllabus, then they can't do it. So we don't want this kind of kid.
Yeah. Yeah, perfect. So we are nearly done, I think. Yeah, we are done with the deep learning part, and just a quick one. So let's say I have a several models trained for my training data set, but then how can we pick which one is the best? It's different situation as the overfitting kind of stuff. Okay, so I have a models. I wanna compare their performance. So there are very commonly used metrics called root mean square error, or MSE, or maybe maximum absolute error, mean error, absolute error. Yeah, there can be several, but I'll use some of them for our use case, like stock prediction.